In this paper, we solve a question on tree automata theory which has been open for a long time, that is, the homomorphism problem. To this end, we develop several constructions and techniques which are interesting by themselves and solve other nice related problems. Our results also have connections with other areas like XML. In order to make this talk accessible to a broad audience, I will spend most of the time by recalling basic concepts on tree automata theory and explaining the problems we solve. In a minor part, I will talk about the techniques we use. Nevertheless, I consider them interesting and encourage everyone to read the paper in detail. So, I start by recalling basic concepts on word automata. This is the classical example of a deterministic finite automaton recognizing the set of words over AB having an even number of A's. It starts from the initial state. It changes of state according to the transition corresponding to each input symbol. It accepts the input word if the accepting state is reached after reading the word. A deterministic finite automaton can also be represented by a set of word rewriting rules. Each rule indicates for each state and each symbol the resulting state. An execution corresponds to a derivation using the word rewrite rules. We start from the initial state concatenated with the input word, and the word is accepted if we reach the accepting state. A language recognized by a deterministic finite automaton is called regular. Working with regular languages has several benefits. They are expressive enough in different settings, are closed under many natural operations, and there are efficient procedures for deciding most of their interesting properties. In this paper, we focus on homomorphism. Our homomorphism is any function h relating words which commutes with word concatenation. Alternatively, any homomorphism can be recursively defined by equations of this form, by specifying the image of each word depending on the first symbol on the word. The result must be specified by a word followed by the image of the rest of the input word. In addition, the image of the empty word must be the empty word. The advantage of homomorphic transformations on word languages is that they are regularity preserving, that is, the image of a regular language by a word homomorphism is also regular. In some contexts, terms or labeled trees are more suited than words to express structured concepts. In a similar way to the definition of automata for words, one can define tree automata for trees. A bottom-up tree automaton is a set of tree rules of this form, where the leaves and the result are state symbols, and the F is an alphabet symbol which can be used for labeling some nodes of an input tree. Additionally, we must specify the set of accepting states. For example, consider the tree automaton defined by the following rules, where Q0 is the only accepting state. It runs bottom-up on an input tree like this one by successively applying the above rules. In a first step, we apply these rules at the marked position, getting this new tree. In a second step, we apply this rule at this position, getting this new tree. Finally, we apply this rule and reach Q0 so that the initial tree is accepted. Our tree automaton accepts the tree language of terms having an even number of A's. These are some contexts where tree automata have been useful. For example, in circuit verification, tree automata are used for computing reachable and unreachable sets of configurations. In XML, types are usually represented by tree automata. In computational linguistics, tree automata are used to compute minimal readings of input sentences. They have also been useful for proving the decidability of several logics, for solving equations like, for example, set equations, and have provided many results in the context of term rewriting. Regular tree languages have almost all advantages of regular word languages. Nevertheless, they are not closed by homomorphisms. In the case of trees, homomorphisms can also be defined as functions commuting with a natural tree operator, that is the application of substitution. Alternatively, a tree homomorphism can be recursively defined by equations of this form. In this case, the image of the tree being only the symbol A is A itself, the B's are converted into A's, and this is the recursive case. The image of f of two subterms is G applied to the image of the first subterm but duplicated. This is an important difference with respect to the case of words. Tree homomorphisms can duplicate images of the rest of the term. As we will see, this is why they can produce non-regular images. Look at this example of the recursive application of h to compute the image of this term. Note that at each application of the recursive case, we are duplicating the left child. The result is a complete tree of height 2 using G's and A's. In fact, the image of all terms through this tree homomorphism is the set of complete trees over G and A. It's not difficult to prove that this language is not regular, since at each node the state should check equality between both subterms, which is not possible with finite memory. In general, nonlinear tree homomorphism like this one may produce non-regular images. The Hom problem is defined as follows. The input is a regular tree language described by a tree automaton and a tree homomorphism. The question is whether the image of the language through the homomorphism is also regular. This paper of Jim Thatcher is one of the first defining tree automata and tree homomorphisms, and shows that Hom is decidable for linear tree homomorphisms that are the ones described without duplicated variables. Other particular cases of Hom have been proved decidable, and these are the most significant to my point of view. Also, slight generalizations of homomorphisms make the problem undecidable, like for example when one considers tree transducers. In the path of solving Hom, we have used techniques and results related to extensions of tree automata. A well-studied case consists in allowing constraints in the rules, imposing equalities or inequalities between subterms pending at certain positions relative to the rule application place. This is an example of tree automaton with equality constraints. This constraint imposes that the first and the second subtrees must coincide for the application of the rule. Look at this example of execution. After applying the first rule 4 times, we reach state Q at each leaf. In this step, we apply second rule twice. This is possible because the terms pending at both childs of the root application place coincide. This rule is applied again in a last step to reach Q. Note that this automaton recognizes the set of complete trees over G and A, which is not regular. Thus, with constraints we gain in expressiveness. In this way, we denote the class of tree automata with equality constraints, tree automata with inequality constraints, and tree automata with equality and inequality constraints. The gain of expressiveness comes with the loss of good computational properties. For example, emptiness and finiteness are undecidable for tree automata with equality constraints, but still decidable for tree automata with inequality constraints.